All right, starting lesson 9.6, C, counting principles. All right, first concept we're going to cover is that of combinations. All right, so in the previous lesson you learned about permutations, where order does matter. For combinations, the order does not matter. All right, so the example below shows that we have a set. Whenever you see these types of brackets used, that's known as set notation. And we have these three elements in it. Now it doesn't matter how the elements are ordered. Okay, so ABC, BAC. The elements in the set are the same. So we don't count this twice because it consists of the same elements. All right, so that's what you have to take into account when you're working with combinations. So note, combinations can be applied to card games, and we're going to get into that in a moment. For example 1, in how many different ways can two letters be chosen from the letters A, B, C, D? Okay, so I could choose A and then B, and I could have A and then C, I could have A first, then D, then I could have BA, then I could have BC, then I could have BD, I could have CA, then CB, then CD, I could have D, then A, then I could have D, then B, and D, then C. Okay, now notice every ordering here repeats twice. Okay, so we have AB is the same thing as BA, and BC is the same thing as CB, and CA is the same thing as AC, and DA is the same thing as AD. Or that sort of looks like the one I had before. That doesn't help. Anyways, then I have BD, and I have DB, and I have CD, and DC. Okay, and DA and AD, maybe I'll do this. Now I could tell them apart. Okay, so how many different orderings do I have here? All right, because the combinations, the order does not matter. AB is the same thing as BA. So all I have to do is count the number of shapes that I have here, and that's 6. All right. And another way to look at it is, well, how many letters do I have to choose from for the first letter? 4. How many letters do I have to choose from for the second letter? 3. Okay? But since the order does not matter, there's going to be repetition then. And how do you account for the repetition? Well, how many letters are you choosing? You're choosing 2. So you divide by 2, factorial in this case, and you will get the answer, 6. All right. Now that leads us into the big formula that we'll be using. There's a permutation formula, and there's a combination formula. And the only difference between the two is this here for the combination formula. So this is the permutation formula right here. And then if you want to know the combinations formula, you just add on the r factorial. Because the r factorial is going to cancel out all the repetition because the order doesn't matter. For example 2, for a certain experiment, 4 students are randomly selected from a class of 20. How many different groups of 4 students are possible? Okay, well, setting up the combinations formula. All right, because does it matter in what order the students are selected? No, it doesn't matter. So we're working with a combination. So I'm choosing from 20. I'm selecting 4. All right, then I have 20 factorial over 20 minus 4 factorial times 4 factorial. All right, so I end up with, use a little strategy to work this out by hand here. All right, I got 4 times 3 times 2 times 1. All right, so 4 goes in 4. I got 5 there. 3, that's 6, I got 2 goes into 6, that's 3. 16 factorials cancel out. All right, and if you were to work this out, you get 4,845. All right, orderings, where the order doesn't matter. Here, oops. All right, example 3, we're working with a card game now. A standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? After the cards are dealt, the player may reorder them, and so order is not important. Okay, so with poker hands, the order doesn't matter. That means we're working with a combination problem. So I have 52 cards to choose from, and I'm choosing 5. All right, so just applying the formula now. 52 minus 5 factorial times 5 factorial, and that equals 2,598,960. All right, that's all there is to that. All right, for the next example, you're going to have to think a bit more than you did for the previous examples. You are forming a 10-person committee from 9 women and 12 men. The committee must consist of 5 women and 5 men. How many different 10-member committees are possible? All right, so essentially there's 2 different groups. There's going to be a group of women that you choose. There's going to be a group of men. All right, so women and men. All right, for the group of women, how are you going to form that group? Now, is it a combination problem or a permutation problem? Now, does the order in which you choose the women matter? No, it doesn't. Okay, so I'm choosing from 9 women. I'm going to be picking 5 of them. And for the men, I'm going to be choosing 12 men, and I'll be picking 5 of them. All right, and you multiply these values because the group of women and the group of men, they belong to the same group. They're all together. All right, so now I apply the formulas. All right, and then I have 99,792. All right, that's all there is to it, because this turns out to be 126, and this is 792. Okay, on to the last example. All right, how many different full house poker hands are possible? Okay, now a full house poker hand consists of a 3 of a kind, and it consists of a 2 of a kind. And 2 of a kind means the same rank. Okay. Now, if you look at your yellow sheet, it lays out all the different terminology for card games in the game of poker. Okay, so for 3 of a kind, how is this going to work exactly? All right, this is where you're going to really have to push your thinking initially, and once you get familiar with this concept, then it's going to be easy to figure out the probability or how many different hands there are for the various poker hands. Okay, so for 3 of a kind, first thing I need to figure out for this 3 of a kind is what is the rank I'm working with. Well, how many different ranks are there? There are 13 different ranks. So from those 13, I'm going to choose 1. Now, after you've chosen that rank, there's 4 cards in that rank, or 4 suits in that rank. So from those 4 cards, I'm going to choose 3 of them. All right, and that covers the 3 of a kind. Now I go to the 2 of a kind. Now I already picked 1 rank for the 3 of a kind, which leaves how many ranks to choose from? There are 12 ranks left to choose from. And from those 12 ranks, I'm going to choose 1. Now, once I've chosen the rank, same thing as before, how many cards are within 1 rank? There's 4, because there's 4 suits. All right, diamonds, hearts, spades, and clover. All right, and I'm going to be choosing 2 from those 4. All right, then you just apply your formulas, just like we did in all the previous examples. And I'm going to get 52 times 72, which gives me 3,744. Okay. Now, it's actually a very easy concept once you understand how to approach the problems and you're able to identify, are you working with a permutation problem or are you working with a combination problem? It just takes practice, and then it'll begin to stick, and then it'll be very easy to identify which formula you need to apply. Now, if you have any questions, make sure to ask. Begin the assignment at the bottom of the page.